Welcome to lecture 22. This is week 5 and we are talking about unconstant single variable optimization methods and applications. So, we have given a brief introduction to the general structure of the optimization algorithms that we will be using for unconstant single variable optimization. So, today we will go into more details. First, classify the various optimization methods that are available for unconstant single variable optimizations. After the classification, we will start talking about the methods in more details. We will also take examples so that you understand the idea behind these methods better. So, this is the agenda for week 5. In the previous lecture, we have talked about general principles of optimization algorithms. Then we will talk about two different types of methods, or in other words, we will broadly classify the methods for unconstant single variable optimization into two categories. One is direct search methods, other is methods requiring derivatives. And we will talk about bracketing methods, exhaustive search, region elimination methods such as interval halving, Fibonacci search, golden search methods, etc. under direct search methods. And we will talk about Newton-Raphson method, bisection method and second method under methods requiring derivative. So, today we will first classify these techniques into direct search methods and methods requiring derivatives, and then we will discuss direct search methods such as bracketing method, under which we will talk about exhaustive search method and bounding phase method. So, in previous weeks, we have learned how to determine whether or not a given solution is optimal. So, given a problem and given a solution, we are now able to determine whether the given solution is optimal or not. We can do that by the application of condition of optimality. Now, we will learn how to determine the optimal or the candidate optimal solutions numerically. It is important to be familiar with numerical methods of optimization, because it will not be always possible to solve an optimization problem analytically. So, it is extremely important that we are familiar with the numerical methods available to us. It will not be possible for us to discuss each and every numerical methods. So, we have selected certain numerical methods that are more popular or more useful, and we will restrict ourselves to those numerical methods only. The single variable optimization methods may be broadly classified into two categories: direct search methods and methods requiring derivatives. The direct search methods are also known as zero order methods. They do not use any derivative information. They use only objective function value information. There are two important class of methods under direct search methods: bracketing methods and region elimination method. Bracketing methods, as the name suggests, brackets the minimum or the optimum between an upper bound and a lower bound, and region elimination method can be used to find this interval of uncertainty. Methods requiring derivatives are also known as descent methods. These methods use information on objective function value as well as information on the derivative. Some methods require only information of first derivative, other methods require information on first derivative as well as second derivative. So, accordingly, the methods requiring derivatives or descent methods can be categorized as first order methods. The first order methods use the objective function value and the first derivative information, whereas second order methods use objective function value, first derivative information as well as second derivative information. Now, we will start our discussion on direct search methods. Let us briefly talk about again unimodality of functions and how the information of the unimodality is used to bracket the optimum or bracket the minimum. Mostly we will be talking about minimization of a problem. As we have discussed earlier, that minimization of a problem and the maximization of a problem are mirror image to each other. Several optimization methods require that the function to be optimized be unimodal. It means that the function has only one local minimum or maximum in a given interval. Look at the figure shown, it is an unimodal function. The minimum is indicated by x star and there is only one minimum over the region of x, the function has been shown. A function of one variable is said to be unimodal if given that two values of the variable are on the same side of the optimum, the one nearer the optimum gives the better functional value, that is the smaller value in the case of minimization problem. So, if you consider this point and this point and both the points are on the same side of the minimum or optimum x star. Since we are minimizing the problem, note that this point which is nearer the optimum has function value less than this point. This is true for unimodal function. So, you can define an unimodal function as follows. A function f x is unimodal if x 1 less than x 2 less than x star implies that f of x 2 is less than f of x 1, where x star is the minimum point. So, what it means is, if I consider this as x 1, this as x 2 and this is the x star, here x 1 is less than x 2 which is less than x star. So, note that the value of f of x 2 is less than the value of f of x 1. Again, if x 2 is greater than x 1 greater than x star, it implies that f of x 1 is less than f of x 2. So, here I take x 1 here, I take x 2 here. Again you see here x 2 is greater than x 1 is greater than x 2, and f of x 1 is less than f of x 2. So, this is an unimodal function. Now, let us talk about exhaustive search, which is a bracketing method. In this exhaustive search method, the optimum of a function is bracketed by calculating the function values at a number of equally spaced points. Look at the figure. The optimum lies between x 0 and x f. This region has been divided by a number of equally spaced points. Now, you can find out the function values at each of these points and then can find out between which two points the minimum has been bracketed. Let the function is defined on the interval x 0 to x f and let it be evaluated at 8 equally spaced interior points x 1, x 2, x 3, x 4, x 5, x 6, x 7 and x 8. The minimum must lie, according to the assumption of unimodality, between points x 5 and x 7. The assumption of unimodality guarantees that the minimum lies between points x 5 and x 7. Thus, the interval x 5 x 7 can be considered as the final interval of uncertainty. This is the simplest of all other methods. So, let us discuss the algorithm for exhaustive search method. Let us indicate n as the number of intermediate points. Look at the figure. My interval is x 0 to x f. So, I divide this interval by n number of intermediate points. So, in the step 1, I set x 1 equal to x 0, delta x, that means the width of each sub interval. Delta x can be computed as x f minus x 0 divided by n plus 1. So, I have set x 1 equal to x 0. So, x 2 can be computed as x 1 plus delta x. Similarly, x 3 can be computed as x 2 plus delta x. Step 2, look at the values of the objective function in these 3 points x 1, x 2 and x 3. If it happens that f of x 1 is greater or equal to f of x 2, which is less or equal to f of x 3, then the minimum point lies between x 1 and x 3. That means, if the value of the objective function is bracketed by the values of the objective function at x 1 and x 3, the minimum point lies between x 1 and x 3. This is again due to unimodality assumption of the function. So, if this is satisfied, we terminate the algorithm, that means we stop. And take the final interval of uncertainty as x 1, x 3. If x 3 is less or equal to x f, we go to step 2 to check whether the condition is satisfied or not. Else no minimum exists in x 0 to x f, or a boundary point, that means either x 0 or x f is the minimum point. So, let us present a very brief analysis of this exhaustive search method. In the interval x 0 to x f, the objective function has been evaluated at n equally spaced points. Those points are x 0, x 1, x 2, x n up to x f. Note that the x 0 is less than x 1, which is less than x 2, which in turn less than x 3, so on and so forth. If the minimum value among the n function values is x k, then the final interval of uncertainty is x k minus 1 and x k plus 1. Please note here. If you say the minimum value, minimum function value among the n function values is x k, then the final interval of uncertainty is determined by one point on either side of x k. That means, x k minus 1 and x k plus 1. This is x k minus 1. So, the length of this final interval of uncertainty is x k plus 1 minus x k minus 1, which can be computed as 2 by n plus 1 into L 0, where L 0 is the x f minus x 0. So, the length or the length of the final interval uncertainty is 2 into x f minus x 0 divided by n plus 1. So, this figure shows you how the exhaustive search method works. The function that we have shown is actually not unimodal, is multimodal. For the time being, you can focus your attention only on this part. And you note that how the region of uncertainty has been obtained. Let us now take an example for exhaustive search method. We want to find the minimum of function f of x equal to x into x minus 1.5 in the interval 0 to 1 to within 10% of the exact value. So, the function is f of x equal to x into x minus 1.5. Although it is not required, but it will help us if I plot this function and see how the function looks like. Particularly, we are talking about single variable objective functions, so we can easily do that. So, I take the various values of x say x equal to 0, 0.1, 0.2, 0.3, 0.4, so on and so forth. Find out the values of the function at each of these x values and then plot this f x versus x. So, if you look at the plot, you can see that a minimum exists between 0.7 and 0.8. So, now let us see how we find out the minimum of this function using exhaustive search method. And we used to find out the minimum within 10% of the exact value. If the middle point of the final interval of uncertainty is taken as the approximate optimal point, the maximum deviation could be 1 by n plus 1 times the initial interval of uncertainty. Please note that exhaustive search method will not give you the exact minimum. It will always bracket the minimum between 2 points. We can go on decreasing the length of this interval. So, we can decrease the final interval of uncertainty, and we need to decrease the interval such that the solution obtained by the exhaustive search method is within 10% of the exact value. Since the exhaustive search method and all bracketing methods for that purpose will always bracket the optimum between an upper limit and a lower limit, the best estimate of the minimum or the optimum will be the midpoint of this interval of uncertainty. So, if the middle point of the final interval of uncertainty is taken as the approximate optimal point, the maximum deviation could be 1 by n plus 1 times the initial interval of uncertainty. Thus, to find the optimum within 10% of the exact value, we should have 1 by n plus 1 less or equal to 1 by 10 or n greater or equal to 9. That means, we must have 9 points. So, I have taken 9 points as x equal to 0.1, 0.2, 0.3 up to 0.9, and we evaluate the function values, and you can see that the minimum is indeed obtained between x equal to 7, x equal to 0.7 and x equal to 0.8. Note that the function value is decreasing as x goes from 0.1 to 0.2 to 0.3 to 0.4, and then beyond x equal to 0.8, as it goes to 0.9, the function value increases. The final length of interval will be 0.7 to 0.8. So, we can take the midpoint, that is 0.75, as the best estimate of the minimum of the function f x equal to x into x minus 1.5. So, here is a homework for you. Let the heat loss from a closed chamber is expressed as Q equal to 1 by x plus 10 kilojoule per hour, where x is the insulation thickness in centimeter. It will cost ₹50 to generate 1 kilojoule of heat per furnace, and insulation will cost ₹100 per year for each centimeter of thickness over the course of its lifetime. What is the optimum insulation thickness that minimizes the total cost of lost heat and insulation? So, you have to calculate the cost of heat loss and the cost of insulation, and then you have to add it up. So, that will give you the total cost. So, the total cost is obtained as this. So, using analytical method, it is possible to find out the optimum. So, you just take the derivative of this total cost with respect to insulation thickness x, set that equal to 0, and you get x equal to 66.18. You check the sufficient condition, take the second derivative, and you see the derivative is greater than 0. So, indeed the total cost is minimum for x equal to 66.18. So, you take this function and find out the minimum of these using exhaustive search. Compare your result with the true optimum x equal to 66.18. Consider a function which is x minus 100 whole square. If x is unbounded, clearly the minimum solution is x star equal to 100, because at x equal to 100 the function value is 0, and since the function value is square of something, it cannot be less than 0. So, how do I bracket the minimum? Several strategies exist. We have already seen one, exhaustive search. So, you can discretize the independent variable x by a uniform grid spacing and then look at the function value, and you can bracket the minimum as we have just done using exhaustive search. We can also use an accelerated procedure where we can make use of this formula to find out the next trial point, which is given as x k plus 1 equal to x k plus delta into 2 to the power k minus 1, where delta is a small constant. So, this will accelerate the search, as we will see soon. For example, with delta equal to 1, the minimum of function f x is bounded between x equal to 63 and x equal to 255 in just 9 function evaluations. So, using this formula and taking delta equal to 1, I can find out the x as 0, then 1, 3, 7, 15, 31, 63, 127 and 255. You look at this part, the unimodality of the function tells us that the minimum is bounded between 63 and 255. So, this way we can bracket the minimum quickly. Next, we talk about another bracketing method known as bounding phase method. Bounding phase method guarantees to bracket the minimum of a unimodal function. Starting with an initial guess, find a search direction based on 2 or more function evaluations in the neighborhood of the initial guess. Then an exponential search strategy is used to reach the optimum. The exponential search strategy is something similar to what we have seen as x k plus 1 equal to x k into delta into 2 to the power k minus 1, which is known as Swan's method. So, in case of bounding phase method, we start with an initial guess, find a search direction based on 2 or more function evaluations in the neighborhood of the initial guess. Then an exponential search strategy is used to reach the optimum. You select an initial guess and an increment, let us call that increment as delta. So, if this f of x 0 minus delta is greater or equal to f of x 0, which is greater or equal to f of x 0 plus delta, then the minimum lies to the right hand side of the x 0. That is true. Consider you have a minimum here. So, you start here, which is x 0. So, you have x 0 minus delta point, and here you have x 0 plus delta. Since function value here is greater than the function value here, then the greater than function value here. So, the minimum lies on the right hand side of the x 0. If f of x 0 is bracketed by f of x 0 minus delta and f of x 0 plus delta, then the minimum lies between x 0 minus delta and x 0 plus delta. Note that f of x 0 minus delta less or equal to f of x 0, which is greater than f of x 0 plus delta, is ruled out by unimodality assumption. It is not possible. If it happens, you will know that there are multimodals. There are more than one mode. It is not unimodal, as the figure shown here. You consider this as x 0, this is x 0 minus delta, and let us consider this as x 0 plus delta. So, note here this is satisfied. So, the minimum lies on the right hand side of the x 0, which is true. But if this satisfies, it will be something like this, where the function is multimodal. For unimodal functions, this is not possible. So, let us present an algorithm for bounding phase method. In the step 1, we set iteration counter k equal to 0, select initial guess x 0 and an increment delta. If the function value at x 0 minus delta is greater or equal to function value at x 0, which is greater or equal to function value at x 0 plus delta, then we choose positive delta. But if the inequality sign is reversed, that means f of x 0 minus delta is less or equal to f of x 0, which is less or equal to f of x 0 plus delta, then we choose negative delta. We choose a negative value of delta. Otherwise, we go to step 1. So, once we have chosen a positive or negative delta, in the step 3, we get x k plus 1 as x k plus 2 to the power k into delta. If f of x k plus 1 is less than f of x k, then set k equal to k plus 1 and get to step 3, else the minimum lies in the interval x k minus 1 and x k plus 1. We have been able to bracket the minimum between x k minus 1 and x k plus 1 when f of x k plus 1 is not less than f of x k. Then we stop the algorithm. So, with this we will stop lecture 22 here.